Sir. Now the forum is hand over to the speaker. Welcome, sir.
Okay, thank you very much for the nice introduction and inviting me for this presentation today. So the presentation will be for 1 hour 30 minutes, or will it be for some time and followed by question answer session?
Yes, sir. At the end of the session, we are planning a Q&A. After
Okay.
1 hour.
Okay. All right. So let's start with the today's session. So today I'm going to talk about extrusion-based metal additive manufacturing. You might have heard a lot about additive manufacturing in general, and specifically you might be knowing that today, as of today, we can definitely 3D print metals. But 3D printing of metals is is a concept, and it's not like that there is only one machine or one technique for 3D printing of metals. There are several techniques. A few you might already be knowing, such as selective laser melting, or popularly known as laser powder bed fusion technique. Or some of you might be familiar with wire arc additive manufacturing. Others might be familiar with direct energy deposition, electron beam melting based additive manufacturing. So there are several techniques which are available as of today for 3D printing metals. But what we are going to focus on today is extrusion based technique for 3D printing metals. Okay. So in the beginning, I have included a brief introduction on what is 3D printing, what is additive manufacturing, and what can be printed, what cannot be printed. And thereafter, we will dive in slightly deeper into the uh, extrusion-based additive manufacturing, metal additive manufacturing. Okay. All right. Let me turn on my laser pointer. Yeah. So additive manufacturing, like you know, it is also popularly known as 3D printing. And in this technique, the components are derived from 3D CAD models. You first develop a CAD model, and then they are built by using a 3D printer in layer by layer fashion. Okay. Now 3D printing is very important and very good technique for designing and printing complex structures. Although there are several conventional and non-conventional manufacturing techniques with which you can manufacture the parts, but when it comes to the complexity of part, not everything can be manufactured with ease with the help of traditional and non-traditional manufacturing techniques. And their 3D printing technique plays a very crucial and important role. So this is one thing that here you can design and manufacture complex structures. Other important aspects include lightweighting and cost-saving components for aviation and automotive applications. For example, if you have to manufacture a part by traditional manufacturing technique, the part is usually solid or say completely solid. But here in 3D printing, what you can do, you can have a part with the varying infill density. Okay, what I mean by that is a part of the material, a part of the structure can be partially hollow, but at the same time imparting the comparable strength as compared to the part which is produced by the conventional manufacturing technique. Now, because we are using less material for filling the structure, it not only saves the cost of metal or alloys, but it also makes the component lightweight. So typically in aviation industry, in aerospace components, in space related um, applications, there you require lightweight components. Okay, so there you can play around with different types of structures, different types of infill structures, infill patterns. Okay, but 3D printing is not only about designing complex structures or lightweighting structures. It can also be applied to more advanced applications such as bioprinting of tissues. So there is another field which is called as tissue engineering. People are 3D printing buildings now. So concrete 3D printing has also emerged as another technique. People are also printing electronics and sensors with the 3D printing technique. So what I'm trying to emphasize over here is that 3D printing, if we talk about sometime around 1998 or around early 2000, at that time 3D printing was more understood in terms of rapid prototyping, where the technique was limited only for prototyping the parts. You had designed a CAD model and you wanted to see how it will look in the real life. So at that time, rapid prototyping was the key element. Thereafter came rapid tooling, where people started making tools with the help of techniques. And today we are focused more on the functional parts or functional components. So what I mean by functional parts or functional components, I mean to say that you can develop or print the part and directly use it in a larger assembly. So the part is essentially not only for visualizing, but it can be used directly as a component in a rocket, or it can be used as a component in a car, or it can be used as a component in an aircraft. Okay. Or if you talk about concrete 3D printing, then you can 3D print house and you can live inside that house. Okay. So some of you might have this notion that 3D printing is just one particular process. But 3D printing is not one process, rather it's a big umbrella. There are several families of 3D printing process. There are several ways to characterize 3D printing processes. Okay. So here what I have done, I have characterized 3D printing processes in 7 broad families. This is the most common classification that you will find in the literature. So based on how you are 3D printing, are you 3D printing with the help of powders? Are you 3D printing with the help of laser? Is there a sheet involved? Are you 3D printing with the help of a filament? Based on these criteria, 7 families are being established, and each of them have several subcategories which have the common working principle or common physics behind the 3D printing process. So here you can see there are 7 families ranging from wet photopolymerization, material extrusion, material jetting, binder jetting, powder bed fusion, direct energy deposition, and sheet lamination. So here in this particular slide, I have only talked about the techniques. I have not talked about materials. So it might be possible that with one technique, you are printing in plastics. With the same technique, with slight modification, of course, you are being able to print in ceramics or in metals, for example. Okay. So these are 7 techniques. My intention is not to go into all these techniques because you might be having some other lectures where you must have gone through these techniques. I will focus only on one particular technique, which is material extrusion technique. Or you, in many places, you will find this term fused deposition modeling, okay, or fused filament fabrication. These are all material extrusion techniques. Okay, so material extrusion means that the material is being extruded for 3D printing of the part. Okay, you might be having, or you will be having, a particular spool where the filament is wound on spool. The filament will go inside the 3D printer. In the nozzle head, the filament will melt and deposit on the build plate, eventually solidify, and in layer by layer fashion, your part is being printed. So this is the crux of the material extrusion techniques. So most of you might have, if you have some experience with 3D printing, you might have done some hands-on with some 3D printer. The cheap 3D printers that you can easily find in laboratories, or you can also buy them from Amazon to as cheap as 15,000 rupees. So these 3D printers, they are all based on material extrusion. And if you have worked with these printers, you might be knowing what are the kind of materials these 3D printers typically use. So you might be printing in ABS material, you might be printing in PLA material, you might be printing in nylon material. Okay. So all these three materials that I have named, they are all thermoplastic materials. Okay, so whatever spools we are buying from Amazon, Flipkart, or from any other service provider, they are typically being sold in thermoplastic materials, or slightly variation of slight variation of thermoplastic materials. For example, carbon fiber infused PLA material. So in PLA polymer, there are short fibers of carbon which are being embedded, or glass fiber reinforced PLA material. So in that, there will be small glass particles which will be there in the polymer matrix. But in principle, if you are doing material extrusion or fused deposition modeling, there you will have one spool, one printer, and the material is being extruded from the nozzle head and deposited in layer by layer fashion. So today we are going to understand how you can convert your FDM printer into for printing metal parts. How we can do that? Is it possible? Is it not possible? If it is possible, how we can change the dynamics and can do this thing. Okay, so this is what we are going to talk about today. I have also made another classification to show you over here that what all can be printed. So like I was talking about, that some people are printing houses, some people are focused on printing tissues, some people are also printing food materials. Okay, so here what I have done, I have written different materials ranging from metals and alloys to smart materials, and I have classified different techniques from those 7 families and subfamilies, that which technique you can choose for 3D printing of a particular material. Okay, so for our technique, I have highlighted this in red color over here, MFF or FDMAT. MFF is metal fused filament fabrication, or fused deposition modeling for metal parts. Okay, so this MFF technique or FDMAT technique can be used for 3D printing of metals and alloys, and also the same concept can be applied for 3D printing of ceramics. Okay, so this is what we are going to focus on today. And of course, you can do 3D printing at micro level, at macro level. Some people also do work on large scale 3D printing, where they are focused on 3D printing of parts which are half the size of a room. Okay, for that a customized printer is required. Okay, so I mean to say that 3D printing can be done at any scale. That is one concept. And of course, there is a wide range of materials which are available today, and there are several techniques which are being available today. So based on the different combinations, you can print whatever you want. Okay, so like I was also explaining to you that in fused deposition modeling, FDM, or fused filament fabrication, FFF, in this technique in particular, what happens? You have a thermoplastic material or composite material. Composite material, why I have written? Because I told you that you might find spools in the form of carbon fiber reinforced PLA material, glass fiber reinforced PLA material, alumina reinforced PLA material. Okay, something like that you can find. That's a composite material, or it can be pure nylon, it can be pure PLA, it can be pure ABS. Okay, or any other thermoplastic. Okay, so there is a thermoplastic material which is available in a filament form, and this filament is rolled on a spool. Then there is a 3D printer, and from 3D print and on in 3D printer there is a nozzle. So this filament goes inside the nozzle, and where it is and melted and solidified. So it is first melted, it goes on the build platform, and then it is solidified in a layer by layer fashion. So this is the most common and most cost effective way of 3D printing. And that is why we are discussing this today, because most of you, if you have slightly worked with additive manufacturing, you might have used this technique. So how we can utilize the same concept, same technique for 3D printing metals is our discussion today. Okay, so here I have just written some advantages. That it is cost effective, it is widely available. So now you can buy these 3D printers for as low as 15 to 20,000. Okay, of course, accuracy is will be in question. What type of materials can be printed will be another question. But what I'm trying to say is that if your aim is only rapid prototyping, where you just want to visualize how your CAD models will look like, you can buy a cost-effective, cheap 3D printer from Amazon, Flipkart, or anywhere. Okay, so here I have shown a graphics from where you can also see that there is a nozzle, and this nozzle is heated. So the filament, when it will come inside the nozzle, it will get heated and it will be deposited on the build plate. This part is called as build plate, and you can see the part is being built in layer by layer fashion. Okay, so worth noting over here is that I have written thermoplastic materials. In the previous slide, I also wrote thermoplastic plus composites. But our intention is how we can 3D print metal parts. How we can 3D print metal parts by combining FDM process. So this is the main discussion that we are going to do today. So when I say metals, I mean metals slash alloys. Okay, so it's not pure metals only. Usually we are focused on printing alloys. For example, stainless steel. So stainless steel is one common alloy that we usually 3D print using this particular type of process. Okay. So first part of discussion in the next few slides is why do we want to do metals plus FDM process? There are already several metal 3D printing techniques which are available, such as laser powder bed fusion, I told you, or direct energy deposition. You might have seen there are a lot of papers on wire arc additive manufacturing process. So when there are so many processes, why do we need to work on a new process, which is metals plus FDM process, or like I told you, MFF, metal fuse filament fabrication process. Why is it needed? So that is also one of the discussion. Okay. Okay. So first of all, I would also like to emphasize one more thing, that how someone will get an inspiration to 3D print metals in using FDM process. So of course there will be one spool that you will be needing, and there will be one 3D printer that you will be needing. So you need to understand how you are going to make the spool, and with that spool how you can 3D print the part. So here I have written one word, MIM. MIM stands for metal injection molding. So you might be familiar with the usual injection molding techniques for manufacturing plastic parts. But there's another variation of injection molding technique which is called as metal injection molding. So our inspiration comes from metal injection molding process. So the way metal injection molding works, the way it manufactures the part, we take the inspiration from there and we try to implement that in our FDM process. Okay. So I was telling you that, so this previous slide has only generic things which we have already talked about. This is interesting. So I was telling you that there are several techniques available in the market. Okay. And one of the popular technique that you know already is selective laser melting, or some people also called it LPBF, laser powder bed fusion. So laser powder bed fusion is a family, and under laser powder bed fusion, there are several techniques. One is SLM, another is SLS, and so on and so forth. So SLM, selective laser melting, it makes use of metal powders, metal or alloy powders. There's a laser. The laser falls on the metal powder, it melts and solidifies it, and the part is being built in layer by layer fashion. Those of you who are working in metal additive manufacturing or have ever tried to print metal parts might understand and know because it uses metal powder and because it is using a laser to solidify the metal powder, it is possible to print structures like these or structures like these. Why I'm saying it is possible? Because both of these structures, they are open structures. So when the structures are open structures, the powder which is not bound, which is not fused, the unbound powder can easily flow out through these open pores. It is very easy. So making open shapes are fine as long as if you want to use SLM or slash laser powder bed fusion, making shapes like this or this is completely okay. But consider the case that we want to make something like a cube. Okay, we want to make something like a cube, and inside that cube, so from outside it will look like that it is a perfectly solid cube. But inside that cube, there is a complex shape like this. Complex shape like this. Can you manufacture it with the help of selective laser melting? The answer is no. Why not? Because the powder will get entrapped inside the part. I would like to show you one part over here. So this is the part that is being produced with selective laser melting. It's a titanium part. Okay, and like you can see that there are some holes that are in here. So this allows for easy flowing of the metal powder. But the parts that are solid over here, the parts that are solid, for example, over here, they are completely solid. They are completely solid. They don't have a structure like this inside, because if they will have a structure like this, the metal powder will get entrapped inside, so it will become very difficult to take them out. So if there is a structure like this is a polymer structure, this is not a metal structure. If there is a structure like this, which is closed from all the sides, so imagine if there is a solid boundary on all the sides, and inside if there is a pattern like this, you will not be able to manufacture it with selective laser melting process. A lot of people who work in the area of 3D printing, they talk about lattice structures. If you are familiar with 3D printing, you might be knowing people write a lot of papers on auxetic structures. Okay, auxetic structures are the structures with negative Poisson ratio. People also work on zero Poisson ratio structure, mixed Poisson ratio structure, where half of the part has got positive Poisson ratio, the remaining half has got negative Poisson ratio. So these type of researches are research work is already undergoing. Why I'm telling you this is because if you want to have a complex lattice structure, it will in metal, it will become very difficult to use the techniques like selective laser melting. Okay, so there we will have advantage, and if we have this extrusion based metal AM process, there we will have slight advantage. Okay. So one thing is you won't be able to produce closed geometries which are hollow from inside in metals using SLM process. Another thing is that the cost of metal printer and the cost of running printer is very high. So if you might have tried yourself for 3D printing of metal parts, or if you might have tried taking quotation from an external vendor saying how much a small part like this will cost, so they might give you a quotation for printing a part like this in titanium. They'll charge you probably something like 25,000 to 30,000. That's the standard rate, or even more if you want to print this part in titanium. Why? Well, what is the reason? There are two main reasons. One reason is that, of course, the machine cost is very high. The machine, the metal additive manufacturing machine sells in the order of few crores. Starting the cheapest Indian machine that I know of sells for 1.5 CR to 2 CR. And if you want to buy a good machine, that will cost you anywhere between 6 crore to 7 crore. The selective laser melting setup I'm talking about. So cost of establishing the setup, that is one challenge. Let's say if you have invested and you have purchased a machine by paying 7 crores or 6 crores, then you have to run the machine. the machine won't run with a small amount of powder. You need to have at least 7 to 8 kilograms of powder. So if you are working with an expensive alloy such as titanium alloy, then the cost of alloy will be very, very high. The cost of metal powder will be very, very high. Okay, because if you even if you want to print a small part like this in titanium, you still have to um, add at least 7 to 8 kilograms of metal powder. Okay, and if you let's say today you want to print in titanium, tomorrow you might want to print in steel. So if you want to print in steel tomorrow, then you have to take out all this titanium powder and then refill again with stainless steel powder, again 7 to 8 kilograms of stainless steel powder, and then again print the part. So this is a cumbersome process, and plus it is also very, very expensive process. And that is the reason why, if you ask for quotation from any vendor, they will charge you hefty amount, particularly if you work in titanium. Why I'm again and again emphasizing on titanium? Because titanium alloys, they are widely used in biomedical applications. If someone is working in the area of implant development, orthopedic implant, for example, okay, there people use titanium alloys. Okay, so titanium alloys are pretty expensive. All right. So that is what is mentioned over here, that although there are several techniques that exist in the literature, such as selective laser melting and electron beam melting, these techniques already exist, but still these techniques are very, very expensive in terms of the establishment cost and in terms of um, cost per part. That is also very, very expensive. You might have noticed that a lot of researchers today, they are working on wire arc additive manufacturing, or in general welding based additive manufacturing methods. Why? Because welding is a well known technique and it is easy to upgrade from welding. But what is the challenge with wire arc additive manufacturing, if you may ask me? So with wire arc additive manufacturing, as of today, if you look into the literature, if you talk to the researchers, they will say, okay, what we can show you that the parts are being deposited layer by layer. That's what they can show you. So they typically report that we have built a wall which is in layer by layer fashion. So that is the current state of art if you talk about wire arc additive manufacturing. If you ask them, can you make a complex structure like this with wire arc additive manufacturing? They will probably say no, because wire arc additive manufacturing, although a lot of people are working today in that, it is extremely difficult to print a structure like this with the help of wire arc additive manufacturing. But good part is that wire arc additive manufacturing is cheap, therefore it is easier to establish. And welding, of course, is well explored, so it is easier to modify. Okay, all right. So these are the things. Okay, so here I have written about MFF FDMAT, metal fused filament fabrication or fused deposition of metal, which is inspired by metal injection molding. So this is something that I always put in my slide, that this technique is something which takes inspiration from metal injection molding, how it draws inspiration from metal injection molding, which parts of metal injection molding are used in this, that I'm going to talk in the next few slides. So before you are being able to understand metal extrusion additive manufacturing, you first should be able to understand how metal injection molding works out. Okay. So metal injection molding is very similar to plastic injection molding, in which fine metal particles replace significant amount of plastic. So in injection molding process, what happens? There are a lot of plastic granules. So instead of plastic granules, there are fine metal powders. Okay. All right. In which fine metal particles replace a significant amount of plastic. So why I have written significant amount of plastic and not all the plastic? Because in metal injection molding, there is not just metal powder, there are also other elements, and these other elements are binder elements, thermoplastic elastomer, and a surfactant. I will go through all these three things. What are these three things? How they are relevant and important. But for now, you can understand that there are three other elements which are present in addition of metal powders, in addition of fine metal powders. The additives and powder particles are compounded using a twin extruder and injected into the mold of the desired shape. The part made in molding is then called a green part. Okay. So first you do a mixing of all these three, four things that I have mentioned, and you then make these small granules out of it. Okay. And then you feed those granules in the injection molding machine. The part that comes out after being injection molded, that is called as the green part. Okay. Then the green part is taken to debinding chamber where the thermoplastic elastomer is removed by chemical and thermal debinding. So because this title suggests metal injection molding, what you want to do? You want to do injection molding of metals, not injection molding of plastics. So everything, listen carefully, everything which is extra in this part should be removed. What is extra in this part? Binder, thermoplastic elastomer, and surfactant. So once your component is made with the help of injection molding process, if you want to work on metal injection molding, all these extra things should be removed in subsequent processing. Okay. And that is why I have written that once this green part is prepared, it is then taken to this chamber called as debinding chamber, where the thermoplastic elastomer is removed by chemical and thermal debinding. I will explain all these things to you. And once these all XYZ things are gone, the final part after debinding is called as brown part. This brown part is then sintered in a furnace vacuum chamber of shielding environment. I will show you one nice picture. This will help a lot to understand. So this is a flow diagram of metal injection molding, and this is the last slide where I'm talking about metal injection molding. Now I'll move to the 3D printing, but this is very, very important and significant for us to understand. So we have metal powder, we have binder, okay, and we do pre-mixing. Of course, I have just written binder over here, but there are other elements such as surfactant is there, okay, surfactant is there, thermoplastic elastomer is there. They are also there. Why they are needed, why they are important, that I'm going to talk about more when I talk about 3D printing. But for now, what you need to understand over here, that these XYZ things along with powder, they are first pre-mixed, then they are fed to an extruder. And what does the extruder do? It helps in mixing and pelletizing. So of course, it will first make a kind of filament which you can cut out and then feed again. So there are ways on how you can obtain different granules. But what you need to understand that from this powder and binder, you are going to obtain these type of granules, which are being then fed to a injection molding machine. So here there is a mold, okay, and all these things, they are being fed to the mold, okay. All right. So once the injection molding process has happened, you want to remove all these parts, the extra parts, but they are not removed in just one step. So here you can see that I have written two steps. One is solvent debinding and another is thermal debinding or pre-sintering. So I will go into detail why these things are needed. But for now, you understand that these things are required. So you first use this process, then you use this process, and you remove all XYZ thing, and then you do the final sintering. And in doing so, after sintering, you will be left with only pure metal part, which you can use for, which you can further use for post process, which you can further post process with the help of polishing. For example, if you want to do some heat treatment on it, for example, hot isostatic pressing, that also you can do on it. So what are the key takeaways from this particular slide, which is very, very important for us, is that first you need to have a proper technique where you can mix all these things. Second is if you talk about 3D printing, how you can 3D print this. Then how you are going to remove all the extra elements by using debinding techniques. And in the end, you are going to sinter it and post-process it. So these are the things that are key takeaways from this particular slide. And now from here on, we will talk about exclusively about metal plus fused filament fabrication, MFF or FD MET. So like I said, this particular technique, FFF technique, FDM technique, it uses a spool. There is a filament, okay, and this filament goes inside a nozzle where it is heated, and it is being deposited in a layer by layer fashion, and the part can be printed in any complexity. Okay, just hold on for a second. Let me have some water. Okay, all right. So this figure 4 FDM printer is the usual printer that you might have also be having in your laboratories, or you might have seen somewhere, or you might have done some hands-on on this type of printer. So first step is how you are going to make this spool in metal. This is the first thing that we need to understand. Once a spool is there, of course, it can be 3D printed with the help of 3D printer. Thereafter, once the part is 3D printed, how you are going to do further subsequent steps, which are debinding and sintering step. This is what we are going to study in next slide. So let's first start with the filament fabrication process. MFF or FDMAT is similar to the MIM process. The difference lies in 3D printing the parts manufactured by these processes. In metal injection molding, what was happening? There was a mold, and inside that mold, all of these pellets, which has got metal plus thermoplastic elastomer plus binder plus surfactant, they are going in. In here, what is the difference? Here there is a filament, a proper filament, and there is a nozzle. So all these elements will go in a nozzle with the in the form of filament. There they will get melted and solidified. Okay. Metal injection molding uses dies to mold and manufacture the green part, whereas MFF FDMAT uses 3D printing technique called FDM or FFF. For AM with FDM technique, filaments are needed as feedstock, fed into the heating element and extruded on the build plate to produce parts. So I hope so far you are with me, you are being able to follow what is being taught. Now you might be thinking that, okay, sir, you have told that we will need a filament, and the filament will go into a nozzle and it will get melted, solidified in layer by layer fashion. But metals have got a very high melting point. So, for example, stainless steel, it will probably melt at around 1200, 1300 degrees centigrade. So, do we need a nozzle that can supply that temperature, or how we are going to do this process? This is something that we need to discuss now. The answer will be that you won't be melting the metal powder or metal alloy in the nozzle. That is not our aim. But then what is our aim? Our aim will be that in the filament, okay, listen carefully, the filament that we are going to make, that will have that will have a specific composition. So that will have metal powder, that will have a polymer base. Okay, polymer can be PLA based polymer, ABS polymer, it can be any other type of thermoplastic polymer. So that is why it is written thermoplastic elastomer. Okay, so it will have some kind of thermoplastic polymer. So when this wire, and of course some other additive, so when this wire or this filament is being fed to the nozzle and the nozzle supplies the temperature, it will only supply the temperature enough to melt your polymer part and not your metal part at all. Okay, so you are going to melt only PLA or ABS. Okay, and the metal powder will be sitting inside somewhere in that 3D printed part. In the next subsequent steps, what you have to do, you have to take away all this polymer part, all this polymer material, and at the same time, you also have to bind this metal powder. And this cannot be done in one step. Why it cannot be done at one step? Because if there was only debinding step, at debinding step you can decide to take away all the polymer, but at that step the metal powders have not fused yet. So what will happen? The part will collapse. That is why you need sintering, because when you do sintering, there you can supply temperatures of the order 1500 degrees, 1400 degrees. Okay. And at that temperature, the metal part can fuse and solidify, giving you the giving you the final metal component, which can be post-processed. Okay, so this is the crux of this thing. You may ask me, sir, is this something that you have developed in your lab, or is it something which is commercially available? So both things are true. There are some few things which are being available and sold commercially in the market. Second is, it's also true that we are developing metal filaments on our own. We are understanding debinding techniques, sintering techniques. So both are true, but you can, if you have a budget, you can of course buy these type of systems which are available from Desktop Metal and Markforged. They typically sell in the order of 1 crore, close to 1 crore, where you can buy a debinding station, a sintering station. Okay, they will also give you filament. So there are some filaments which are also commercially available. BASF and Virtual Foundries, they sell these type of filaments, metal filaments. Okay, especially for 3D printing with this technique. But these companies that I have listed over here, they have a very limited availability of filament, meaning that you might not be getting copper filament, or you might not be getting a high entropy alloy based filament. Okay, they will provide you what they have. Okay, so that is another reason why, if you look into the research papers that talk about metal extrusion based metal 3D printing, you will find a lot of papers that are around stainless steel 316L or 174 pH stainless steel, because these two materials are widely available from BASF. They are widely available from BASF. So people buy this material from BASF and then they start research in using this particular technique. Okay. But our intention in this lecture is not to buy filament from outside. Our intention in this lecture is to understand how I can develop filaments on my own. That is the reason why we are having this session today. So you understand how if I want to prepare a complex filament, how I can prepare that filament. So tomorrow, if somebody wants to prepare alumina, which is ceramic, so alumina-based filament, he can prepare. Somebody wants to prepare copper-based filament, or maybe some other type of alloy, titanium 6 Al4V kind alloy. If you want to print a filament, make a filament out of that, you should be able to understand what will be needed, what kind of research will be required, and how I can make the filament. That is the reason why I have taken the first part as filament fabrication. Understood? So first thing first is how you can fabricate the filament, which is the raw material for your 3D printer. There are several terms that I have used earlier as well. One is thermoplastic elastomer, another is binder, another is surfactant. These terms we have also studied during metal injection molding discussion. So in filament fabrication, yes, all these things will be required. You will of course need a metal powder, okay, because that is the main thing. You will be needing a thermoplastic elastomer, you will be needing binder, and you will also be needing a surfactant. So what are these? They are discussed over here, and why they are important, why someone should use these or not. Metal powder, you already understand. Okay, the okay the if you want to if you want to produce your 3D printer part in stainless steel, you need to have a stainless steel metal powder. One thing that I want to tell you is that percentage of metal powder is very important over here. So let's say if we decide to keep 80% stainless steel, okay, listen carefully. If we decide to choose 80% stainless steel in our filament, then after all the subsequent steps, 3D printing, debinding, sintering, post processing, the final metal part that you are getting that you will get will not have thermoplastic elastomer, will not have binder, will not have surfactant. So it will only have metal powder. But your metal powder was only 80%, it was not 100%. this also means that your part will be 80%. It will be 80% in size, meaning it will be 20% smaller. Okay, so if you want to make 1 cross 1 cross 1 cube, it will be eventually come out to be 0.8 cross 0.8 cross 0.8. It will be 20% shorter. Why it will be 20% shorter? Why it will shrink? It will shrink because these other things, they are present, they make 20% of the composition. And in this process, what you have done, you have taken away all this 20%. So of course, in the end, you will be left with what is metal, how much metal percentage is there, you'll be left with that only. If you decide to keep 65%, sorry for the bad handwriting, I don't have a pen, but if you decide to keep 65% metal powder, of course your final part will be relatively smaller. Okay, understood? So somebody might say, sir, then it is beneficial, we should keep 90% of metal powder or 100% of metal powder. Why or let's say 99% metal powder, and these other things can only be 1%, then it will be beneficial, our part will shrink only 1%. You might have this thought. Well, that's true, but you can't do that. Why you can't do that? Because if you, the more metal powder you fill, the more metal powder you decide to keep, it will be very, very difficult for you to manufacture the filament of that metal powder. Okay. Imagine there is a filament. Okay. Imagine there is a filament which has got complete metal powder in it, or 99% metal powder. That filament will be highly brittle filament. So that moment you touch it, it will break because there is no bonding inside the material. All of it is just powder with some additive. Okay, so there need to be some optimal proportion of binders and metal powders. So that is the reason the optimal percentage that most people keep is around something around 75%. Even at 75%, I can tell you that the filament is still quite brittle. Okay, if you touch it, it will eventually break. But you need to have other elements in it, because otherwise you won't be able to make filament at all. Because I will explain it to you in the next few slides how a filament is being made. But you need some kind of elasticity, you need some kind of flowability. Okay, and that cannot be provided only with the metal powders. That is the reason why we need some other types of materials as well along with the metal powder. Okay, so thermoplastic elastomer will, this helps in giving flexibility to filaments produced. And during shaping or 3D printing, high temperature TPE makes extruded filaments properly bond with previous layers. So TPE or thermoplastic elastomer, in simple terms, it will be your PLA material, your ABS material, or another type nylon material. Okay, and there are two reasons why I'm using this type of elastomer. One, it because it makes the filament flexible, so you will be able to make the filament. And second, when you are going to extrude it, when you are going to put it in the nozzle, and the nozzle will heat up and melt it and deposit it in layer by layer fashion, that will only be done on this thermoplastic elastomer and not on metal powder. Why it will not be done on metal powder? Because thermoplastic elastomers have a glass transition temperature of around 190 degrees, 210 degrees. Therefore, that is the reason if you look at the nozzle, okay, if you buy a 3D printer, always look for the nozzle or the heated nozzle I'm talking about. Uh, to what temperature it can go. So usually these heated nozzles, they can go up to the 230 degrees, 220 degrees, because most of the thermoplastic materials, they change their properties. They melt around 190, 180, maybe 200, and that is the reason if you want to make peak filament, PEEK, peak parts, you need to buy a special 3D printer, because PEEK is a material that will melt at around 400 degrees, 380 degrees. So high-end 3D printer would be needed. Okay, but the elastomers, the thermoplastic material that we are referring to, ABS, PLA, nylon, they all have glass transition temperature of around 180 degree to 200 degrees, or some might be having 210, 215, which can be easily be taken care of. So you have this thermoplastic elastomer, you mix metal powder in it. The usage of thermoplastic elastomer, I hope, is clear to you now. Then you need two things. One, you need surfactant, and one, you need binder. Why you need these type of elements? Why there is a need of binder and surfactant, and not just binder or just surfactant? The reason lies in because you are using two separate processes. One is debinding process and one is sintering process. So in debinding process, what you want to do, you want that once your part is being printed, let's say once your part is being printed, that is metal plus TPE plus binder plus surfactant. So when you debind this, what will happen? You want that a part of these XYZ elements will go away in debinding. Debinding can be done in many ways, by dipping in the solution, by purging in the gas. There are many ways to debind the part. Okay. But when you debind the part, you want that these things, a portion of these things will go away. Maybe the thermoplastic elastomer might dissolve completely. Okay, but you cannot dissolve binder and surfactant at the same stage when debinding is happening. Why you cannot do that? Because at that stage your metal powder is still not fused. You haven't supplied a temperature high enough yet that your metal powder will be fused. So if you decide to take away everything at this stage, if you decide to take away binder, if you decide to take away surfactant and TPA, at the same time, then what will happen? Your part will collapse. So you want that the solvent that you're using, that will eat up only thermoplastic material and leave behind binder. So binder is something that is sometimes also referred to as backbone, because when your solvent is eating up your plastic material, then the binder is acts as a binder is something which is not being eaten up by that particular solvent. So binder stays there. It maintains the shape of the part during this solvent debinding process. Okay, and then in the end you have this thermal debinding. Thermal debinding, at that stage you provide the heat, high temperatures, hot enough to fuse the metal powders. Okay, and at that stage all the remaining things which are binder surfactant, they go away. Okay, I have written one point over here, that why you actually need surfactant. Okay, surfactant help reduce torque requirement during extrusion by decreasing the mixture's viscosity. To understand this point, I want to show you one image. So this is how you are going to make filaments. So this thing is your end product. You need a spool which has a filament, and filament is wound on spool. So you mix all these things: thermoplastic elastomer, binder, surfactant, metal powder, and you put it in this extruder. Okay, so this is extruder that I have shown you is a single screw extruder. It can also be a complex twin screw extruder kind of setup. So over here, what happens? Imagine if there is 100% metal powder. Then if this motor is rotating this screw, this metal powder will of course go ahead, but nothing will happen. This extruder is also heated over here. Heated part, not the metal part. So 70% is metal powder, 30% is your TPE plus binder plus surfactant, and in this 30%, at least 20
Prateek,
Professor?
Uh, Professor, your voice is breaking.
Yeah, Varuvaran,
Sorry,
I think.
something went wrong.
Yeah,
Yes,
yeah,
yes,
your voice
Professor.
is breaking.
Okay, I
It's
think
okay
I
now. It's okay now.
Now it's
should I reshare? You are
It's
not
okay
being
now.
able
It's
to.
okay now.
Nahi, are you able to see my screen or not?
no,
No,
Professor.
no.
No, so that is thing. So I
Nil,
need to
Nil,
reshare.
yes,
Just
Professor, yes. Yes. Now we're able to see, Professor.
okay. Just give me a second. Yes. So you are able to see my screen. Just a minute. Yes. Okay. Yes. So I was telling you that this 70-30 ratio, there should be 28, this 30%, in this 30%, 28 will be your TP and the remaining 2% will be these XYZ things, which are binder and surfactant. So when these things are being poured in the screw, this extruder, the screw's role is to push things forward, okay, and this has got this is of course heated, so it will heat up your polymer and convert it into the form of filament, okay. And the metal powders, if we take a microscopic image of this filament, the metal powders will be uniformly distributed. They will be present somewhere. They will present homogeneously in this filament, okay. So this surfactant, coming back to the surfactant, why do we need surfactant? Because it helps reduce torque requirement. So because there's a motor over here, so motor will rotate and try to push the material forward. You can imagine if there is more metal powder. So instead of 70, let's say there is 90% metal powder. Then metal powder is not viscous material, so it will be very very hard for the motor to rotate the screw and push the things forward. If instead of metal powder it was 100% plastic, so plastics would have melted inside with the help of heated screw, and it will be easier for the motor to push the material forward. But if there is more metal powder and relatively less plastic part, it will put more load on the motor to push the things forward. So that is the reason why we use this additive called surfactant, because these additives called surfactants, they basically reduce the torque requirements of the extruder. Okay, so that's the reason why we use surfactant. Okay, I hope this is clear to you. All right. Okay. So there are several steps which are involved in this. Okay, we can spend one whole day in understanding only about filament fabrication, but we don't have that much time today to discuss on this. So I will touch in briefly how you can make filaments, what is important, how you can debind, and how you can sinter. But otherwise, if we go into the depths of this, it will take a whole day to discuss only about how you can make filaments. So there are several techniques which are available in the literature using which you can make these filaments. Okay. One thing is that you need to have the homogenization. So if you look at this filament, this is basically this only. The exaggerated view, what do you want over here? You want that your metal powders are uniformly distributed. The metal powders are uniformly distributed. It should not be like that in one particular section there are a lot of metal powders, while in other section there is nothing, there is no metal powder and only plastic, because this will create inhomogeneity. This will create a lot of anisotropy in your final 3D printed part. So you want that homogenization of metal powder should be there. So typically what people do, they use something like, for example, twin screws. Here you can see that I have used twin screws. Or if you don't have access to twin screws, what people also do here is that they use single screw. They make the filament, and what they do, they chop the filament. They chop the filament to have this small pellets. These small pellets are being fed again, and then again the filament is being prepared. There it is again chopped, being fed back to the extruder. Again the filament is prepared, chopped, and fed back. So several cycles are of this repetitions happen. Just give me a moment, sorry. So several cycles happen, and after several cycles, usually after 6 to 7 cycles, you start getting the homogeneous filament. Or some people also have this kind of mixing where they use rollers for mixing the part, mixing these small elements. Okay, so your compounding or mixing can be done using twin extruder. It can also be done using single extruder. So here, once you are sure that the final filament that you are getting has got the homogeneous distribution of metals, then what you are going to do, you are going to wound it on a spool, which will look like this. So here I have shown you another type of extruder, which is a piston based filament extruder. So here there is a piston which is pushing everything through a small opening, and the filament is being prepared. Okay, so here I have written few points. Let's go through them. The last and most crucial step of filament fabrication is the extrusion of filaments and winding, in which the compounded feedstock is extruded through the extruder and winded onto a spool using a winder. A significant factor to be considered during the extrusion is the rheology of the feedstock in extruder, which depends on the material selection and compounding. So of course, there are several ways, several techniques on how the rheology can be determined. So that is not the topic of discussion of today, but there are different curves that are being plotted. I can maybe show you just for your interest. Like for example, there's a viscosity curve that is being plotted. There is this another curve where you have some behavior of torque. Some effect of additives can be understood with these torque curves. We're not going into detail of how these curves will be plotted and how we can interpret this, because that is not the agenda for today. But just to give you an understanding that the rheology for these filaments, highly filled polymers, can be understood using different techniques. Okay. Next thing is that your powder that you are using. The powder will also have a role to play. The powder size is the powder content, the powder size, the powder shape. All this has got some role to play in the final filament fabrication. The amount of powder in feedstock affects the rheology of extrusion. As the percentage of powder increases, the viscosity of extrusion correspondingly increases. This is what I was also trying to explain to you in this particular slide, that if you decide to keep 100% metal powder, it will become highly viscous. Someone might say, sir, I want to keep 98% metal and only 2% thermoplastic. Okay, you can keep, but the system will become highly viscous. Your motor will need to it should have very strong motor. It should be able to push things outwards. And again, the point is that if you're using only 2% of polymer, it will be very, very hard to make a filament out of it. So there need to be a sweet optimal value of how much percentage of powder should be there, how much percentage of TPE should be there, how much percentage of binder should be there, and how much percentage of surfactant should be there. So there are studies. And of course, the graphs that I showed to you, it is possible using those graphs to identify all these things. So what are the properties that are being, so okay, I think I missed something over here. Wait a second. Yeah. So for the final part to shrink less and to have high density at the end of the sintering, having the maximum powder percentage in the feedstock is necessary. So of course, the more powder you have, the less shrinkage will occur at the end. But you cannot have 100%, you cannot have 98%, you cannot have 95%. Optimal value is something around 75 to 80%. Okay, so 80% metal is there, 20% will be polymer and other things. Okay, so the final part that will come out after sintering, it will also be 0.8x of what you have designed. But if you know these shrinkage, if you know how much shrinkage is happening, what you can do, you can always map this thing and you can make your part slightly oversized. Okay, at the time when you are designing this in CAD. Okay, because you know that eventually they will shrink down. Okay. Additionally, a feedstock with high powder content produces filament with high inhomogeneity, making them highly brittle. This also I have explained to you that if you decide to keep a lot of powder, then it will be so hard for you to 3D print, because a 3D print, before going to 3D print, it will be so hard for you to wind it on a spool, because at the moment you start winding, it will break easily because it is highly brittle. Okay, so this we have understood. So filament should have low viscosity at high soil loading. Filament, so in the filament, there should be no agglomeration. The particles should be uniformly spread, and it's not like they are clogging the nozzle. It should not be like they have clogged inside. They have formed some lumps inside the filament. This should not happen. Okay, so this should have sufficient stiffness and column strength to act as piston to drive the extrusion during printing. Filament should have sufficient tensile strength for spooling and unspooling, which is windability. So people who work in only development of the filaments, they judge several things. Not all the filaments are printable. So imagine if you are making filament. Okay, this is a filament that you have made, but it is of uneven size. So if your filament is something like this, so to naked eye, it might be looking that it's a perfectly cylindrical, but it's not perfectly cylindrical. And somewhere the diameter is more, in some places the diameter is less. So if this kind of situation arises, then it will become very, very difficult for your nozzle to handle. In ideal scenario, what do you want? You want that your filament should have uniform diameter, and in ideal scenario, what do you want? You have uniform distribution of metal powders. Okay, so we have understood till here, we have understood that how a filament could be made. So once you have made the filament, then you can 3D print the parts. So if you understand material extrusion technique, you, just a second, you might also be knowing that there are different ways of 3D printing using only material extrusion. One way is that you have a spool and you push the spool through a nozzle, and it is melted and solidified in layer by layer fashion, just like this. But that is not the case always. You can also have a piston based arrangement. This is a screw based arrangement, and this is a plunger based arrangement. So in here there is no spool at all. So here there is your mixture, and there is a motor, and this pushes out through this heated nozzle, and the part is being fabricated. Here you have something like a piston type of arrangement. So there are different ways to do this, but in today's discussion, we'll focus on something like this only, where you have understood how this will be fabricated. And once this is fabricated and it has got good flexibility, it will be easier for it to go to the nozzle and print the part in layer by layer fashion. So this is the SEM images of the 3D printed part. The part exactly looks like this. You will not be able to tell that where there is polymer, where it is metal. It is all mixed in here. Okay. So thereafter, once you have done this, then you will go to the dewinding stage. So I have written down some points over here. Okay. Sorry. Okay. So if you see this, sorry, if you see this image over here, you can see some patterns are being made over here. Okay. So these patterns are possible to be made because you are designing all these things into the CAD geometry and then 3D printing it. So once you have printed this part, before I go to the debinding, I want to talk slightly more on the green part only, the post-processing of green part. Sorry, the post-processing of the green part. So if you look over here, how you can post-process only the green parts and why they are important. I have shown a nice image over here. A lot of researchers, they work in hybrid additive manufacturing. Okay, if you look into the literature or if you look into what other people are doing, people are using additive plus subtractive manufacturing. So how you can implement that in this particular scenario, I can tell you. So you can have the at the time when your metal part is extruding, when your metal plus polymer part is extruding from the nozzle, uh, if there is a setup which can do milling or which can do some machining, you can do the machining at the same time over here. Then again, you do the extrusion. If you want to do some machining at the same time, you can do that. That is also possible. Only on the green part, only on the green part, not on the sintered part. So this multiple iterations can be done. A complex shape can be made, which can be finally then sent to the debinding and sintering step. So over here you can have a solvent bath and a furnace for debinding and sintering the parts. So in that way you can combine subtractive and additive manufacturing. Okay, in this particular case, okay, I'm only talking about this metal FFF plus plus subtractive techniques. You may ask, sir, why somebody would like to do this, why somebody would like to combine this. Somebody would like to combine this because it is easier to mill out this polymer plus metal mixture, polymer plus metal part, compared to if you would have only solid metal part. It would have been very, very difficult to mill out, not very, very difficult, but relatively difficult to mill out the solid metal part. So once this is done, then what do? You have to do debinding, okay, removal of these TPE, thermoplastic elastomer. So this process aims to remove the polymer binder after printing to create a brown part, a skeleton of metal powder, which is ready for sintering. Okay, now what happens if you do not remove, all the TPE material, if there is some TPE material which is being left and you put it into a furnace, what will happen? It will form some blisters or bubble-like structures. Why this is the case? Because if you try to understand the physics behind it, I have drawn a very nice image over here. So let's say if you have a green part over here, okay, there's a green part, and there is of course this metal powder. There is the red thing is your thermoplastic elastomer. Okay, then there is some surfactant binder, all these things. So when you do the debinding on it, so when you do debinding, what happens after 4 hours of debinding? You can see that some white spaces have started to appear. After again 4 additional hours, 8 hours of debinding, you can see that additional white spaces appear. After 12 hours of debinding, you can see that this white space has appeared more. This implies that during the solvent debinding stage, what is happening? Your extra voids are being created. And why these extra voids are important to us? Because when we put everything into the furnace, whatever is being left, they will eventually come out through these gaps only. Imagine if there was no gap on the boundary. Imagine if this boundary was closed and you put everything into the furnace directly without going into the solvent debinding. In furnace, the temperature will be around 1400, 1500 degrees. And there is no way for the plastic to go out because of this solid boundary. So then what will happen? These kind of blister formations will occur. Okay, that is why it is very, very important that you know your process very well, that how much binder you are trying to remove. Okay. In the literature, these terms are being used interchangeably. Somewhere they use binder, somewhere they write somewhere they use this term binder, somewhere they use term surfactant. So, but they are different. Binder is different, surfactant is different. Yeah. So this you have understood that solvent debinding, once it is being debound in a solvent, it will create open pores, and this will help the other material to go out very easily. Here I have shown you some of the nice SEM images, which are not my images, they are taken from some reference. Okay. Okay. Thermal debinding, what happens after this? So after this, what happens is that you put everything into the furnace, and because you are giving such high temperatures, because you are giving temperatures of the order 1500 degrees, 1600 degrees, at that stage, what happens? All this metal powder, they will start to melt and start to fuse basically. Okay, so it will start to fuse. I can show you some nice image over here. This is a sintering stage. It's a two-sphere sintering model. Your initial metal powder was looking like this. As soon as you put it into the sintering furnace, when the temperature increase slightly, this fusing happens and the metal powder gets joined. So here you can see that we have the brown part, which is being obtained after the debinding. And when you are doing the sintering, the part is, of course, shrinking. The metal powders are being fused together. And in this, you will have only the metal powders. And of course, this part will, because the way it is being manufactured, it has got some part porosity in it. So part porosity is something that we cannot avoid in this. Okay, so this is how the sintering is done. So sintering is again a very, I would say, detailed topic, because sintering, they have different types of sintering furnaces available, tube type furnaces. There's a big oven type sintering furnace that is also available. Whether sintering should be done in a inert environment, should be done in vacuum, should it be done in oxygen? This is again another thing. It should not be done in oxygen, because if you do it at room environment, what will happen? The oxygen will react with the metals and alloys, and it will form metal oxides. Okay, so your part will eventually get corroded. Okay, so that is the reason why it should always be done in either vacuum environment or in inert environment. So here I have tried to summarize this entire methodology, starting from filament fabrication. So once you have made the filament fabrication, there's this big black box in between, which involves your 3D printing, your solvent debinding, thermal debinding, and then your final metal part is obtained, and then there is post-processing. So when you make the filament, this filament will go into this 3D printer. If it is 3D printed, you can see this gray thing is powder, and this green thing is backbone, and this light green thing is soluble powder. So the soluble powder, eventually when you do solvent extraction, you can see this soluble binder, it goes away and white spaces are being formed. These white spaces are being increased, and when you put it into the furnace, whatever is there is backbone, that is also gone, and in the final sintering there's only metal powder, and it eventually solidifies and form the final metal part. And then if you want to do some post processing, any heat treatment is required, any polishing is required, that can also be done at this stage. So this is the entire crux of how you can 3D print metal parts using the metal extrusion technique. So before I finally close this lecture, I have one small announcement. I will also take questions, but before that, I would like to go through this announcement. So I am hosting a short course in the next month, which is from 5th December to 9th December. It is about mastering 3D printing from basics to advanced techniques, and this will be offered in hybrid mode. So theory lectures will mostly be done online, and the lab sessions will be for lab sessions, you have to come to IIT Mandi. It will be on campus, okay? And it is for everyone, students, faculty members. If you are working on a startup, it's for you as well. So if you would like to participate in this course, if you want to do it in online mode, that is also fine. If you want to do it in a offline mode, you are welcome to come to IIT Mandi, and you can do some hands-on experience, hands-on experiments. The lectures will be delivered. Of course, I'm the main course coordinator, and the lectures will be delivered also by me and by other faculties from IITs and IITs. There are also some foreign speakers and industry persons from Germany and Denmark, so they will also be delivering the talks in there. Here I have written a very brief description of what will be included in theory session, because if you look at the title, it says Mastering 3D Printing from Basic to Advanced. So we'll talk about everything in this, everything that you need to know about 3D printing, starting from what is 3D printing, tips and tricks of CAD models, how you can build efficiently, build CAD models, how you can repair CAD files, all those things, different introduction to all the techniques. So I showed you 7 families. We'll talk about all those families. Then we'll talk about fiber reinforced polymer composite 3D printing, how you can embed a continuous thread of glass, a continuous thread of carbon, a continuous thread of Kevlar into a polymer matrix and 3D printed. We'll also talk about biomedical side of 3D printing, 3D printing of implants. We'll talk about 3D printing of wind turbines. We'll talk about tissue engineering, how you can 3D print tissues, and tissue engineering will eventually lead to organ 3D printing. What is bioprinting? How does a bioprinter looks like? All these things we will talk about. There will also be one lecture on extrusion 3D printing, which we have done today. So this will eventually be something like this only. Then if you want to build any startup, then how you can take advantage of 3D printing and building that startup. So that will be all about theory sessions. Lab sessions are slightly more interesting if you want to attend those. So there will be training on 2 softwares. One is Mimic softwares and one is COMSOL, training for 3D printing simulation. So how you can use FEM for doing simulations in metal 3D printing, composite 3D printing. That will teach you in these 2 sessions. We will also teach you over here how you can make your own filaments. If you want to make metal filaments, we'll show you how you can make metal filaments. We'll also show you how you can make only pure polymer filaments. So pure polymer filaments are slightly easier to make. Some people, if you look into literature, people work in putting into, let's say, jute fibers into polymers or sawdust into polymers, making sustainable filament. So how you can make filaments like these, we'll show you those and we'll train you on those. We will then teach you some hands-on exercises on 3D printing of plastic parts, 3D printing of fiber reinforced composite parts, and how to 3D print metal parts using FDM printer. So when you come here, we'll show you how you can debind the parts, how you can sinter the parts. We have sintering furnace over here. We have a filament extruder here. We have a composite 3D printer. So we'll show you all these things. And the registrations fees will be different for different things. So if you are only taking theory sessions, it's slightly cheaper. Lab sessions plus theory sessions slightly expensive. Not expensive, but slightly more than the theory session. But this will also include your food and stay at IIT Mandi. So we'll be hosting you over here. We'll be covering food for all the 5 days, all meals. So the registrations will open from 8th of November. Okay, so today is the 6th, so in 2 days the registrations will open. And of course, I cannot send emails to all of you. So I have put my LinkedIn QR code over here. You can take a screenshot, you can take a photo, you can scan the code. So this code will lead you to my LinkedIn profile. You can connect with me on LinkedIn. And of course, on 8th of November, I will post all the details, the fees and everything will be posted. The detailed curriculum will be posted, and how you can register, that will also be posted over here. So that is why I thought of putting in QR code over here. Feel free to take a screenshot or photo of this QR code and try to follow me on LinkedIn. So that was all about today's lecture. So this is all references. Thank you very much for inviting me. And now we are open to questions. If anybody has anything to ask, feel free.
Thank you, Professor. Thank you for your insightful session. I have a pile of questions from the audiences. I'll share
Please
one.
go.
Can we use MIG wire as filament in metal filament additive manufacturing? MIG wire, MIG.
MIG wire, no, you cannot use, because here we are not talking about pure metal filament. See, if you want to use a pure metal filament, say tungsten wire, for example, if you want to use tungsten wire into your extrusion in your FDM printer, no, you cannot use that, because the nozzle that we have talked about, the heated nozzle, that can only go up to temperatures of 200 degrees to 230 degrees. At that temperature, your metal filament won't melt. So for that, we have another processes such as wire arc additive manufacturing, for example, where you can use metal wires. Here you can only use polymer based metal filament, because the polymer will melt into the nozzle. Yes.
Can we compare the strength of the material produced with the MFFF with other AM processes?
Yes, of course we can compare. We typically do tensile testing, flexural testing. We do compression test, shear, torsion, depending on what you want to compare. But of course, if you want to write a journal article, this is something that you can also consider doing, where you can compare the strength of all these things. You can also do the experiments only on green part. You can also do the experiments on the final produced metal parts.
And one more question: how can we measure the density of the material? Will it be equivalent to the other AM metal AM processes?
Yes, so it will be compared to the other metal AM processes. So it will be comparable to laser powder bed fusion process. This is a good question. How you can measure the density? The way I usually do density measurements is by using CT scanning. So with the help of CT scanning, industrial CT scanner, it is easier to identify the different voids which are there in the structure, the size of the voids, the location of the voids. So not only you will be able to get the density measurement, but you will also be able to get the exact location of the pores. Another way to do this is you can make a, let's say, a solid cube of a certain dimension, and then you can print the same cube by using this technique, and then you can compare the density between two to get the accurate density measurement of this. Okay, so you know the volume and you know the mass, and then you can find the density.
And one more question from Santosh Kumar:
So
the melting temperature of binder
Yes.
and the melting temperature of the binder and subtractor is very low as compared to the metal. So the filament will not have sufficient strength to fit into the machine. How can we overcome? So
Can you please repeat the question?
Yeah,
the
melting temperature of the binder or the polymer is very low when compared to the metal. While we making the filament, the strength is,
yes.
Will it be sufficient to fit into the machine?
Yes, because you see, when you're making the filament, you are not melting the metal powder. You are only interested in melting the plastic part. What you are interested in is that the metal powder should get homogeneously distributed in the entire filament. So if there is highly filled polymer, if there is more metal content, which has not even fused inside the filament, you touch the wire and it will break very easily, because there is no strength in it. So the strength will eventually come from the polymer part. So you see that I just for the comparison, I have this charger wire over here. So this charger wire has got a lot of strength in it. Okay, imagine if this charger wire was made of completely metal powder, and the metal powder has not solidified inside it. So the moment I touch it, it will eventually break down. So there is no flexibility in it. So you will not be able to feed it at all into the 3D printer.
So can you please suggest what is the maximum percentage of reinforcement is allowed in making a wire?
75 to 80%. So there's no hard and fast rule, like I said. So this is what I know from the experimental data and from the literature review. Typically, people keep 75. They report that they have 75 to 78% of metal powder, the commercial suppliers. But if you try to make your own filament, you might realize that even 75% is very, very high. So something around 65 to 66% is a reasonable number at which you are able to get a reasonable good flexibility and reasonable strength of filament.
And one more interesting question. Can we tailor filaments like nano powder filled filaments?
Yes, that you can also do. You can decide, like I was in one of the slides, I was talking about that metal powder can have different shapes and different sizes. You can decide to choose nano size metal powder. What will be the challenge in the nano size metal powder? If you have worked with nano size powder, you know that they tend to agglomerate, they tend to
Agglomerate,
form
yeah.
lumps. So when you will put into the extruder, what will happen is that they will form small lumps inside the polymer matrix, and that is not our intention. Our intention is that it should be homogeneously distributed in the filament. So you can of course use, in principle you can use nanoparticles, but at the same time you need to identify a way how these nanoparticles can be uniformly distributed throughout the filament. So it might be that once the filament is made, you chop it into very, very, very small parts and then again feed it. Okay, this can be one way. Another way could be maybe using a twin extruder or something like that. Okay, so this is how you can probably do that.
And one more participant asked, is it commercially available, the filament?
Yes, yes. So the filament is also commercially available. And like I said, that BASF is one supplier, Virtual Foundry is another supplier. But the choice of material is very, very limited. So BASF, like I know, they sell stainless steel 316L and 174pH steel. So these are two materials commercially available. Virtual Foundry has got slightly more options. You can also buy copper filled filaments, aluminum based filaments, but not everything is available. So that is why it is very, very important that you understand how a filament fabrication is being done, because then you can make everything on your own. So what is the that is why we have discussed a lot about filament fabrication today.
So what about the strength of the metal browser when compared to the conventional material? We are having here some chemical processing and all that.
Yes, so when we are doing solvent debinding over here, where we are dipping everything into the chemicals, so this solvent is something which is non-reactive to the metal part, but it is highly reactive to the polymer part. So
Polymers.
when the polymer plus metal will be dipped into the solvent will only eat up whatever is polymer there, and it will not attack the metal. If you talk about the strength, so the strength of the parts that you get from this process is very much comparable to the part that you can make with laser powder bed fusion process, okay, or another comparable process. But if you want to compare them against the conventional parts, maybe casted parts, for example, then of course, if you are making it with conventional manufacturing, which has got even casting parts will have high porosity if you talk about sand casting, but there are ways to reduce porosity, like in high pressure die casting, you can reduce porosity a lot. So the less porosity is there, the better will be the strength of the parts. But if you compare among the family of AM processes, I would say that this is very much comparable to what you will get out of other AM processes.
So you also said about the you also said about the shrinkage. If we fabricate what's 10 centimeter, we will get 8 centimeter, right? Is it common for all, or it will vary with different metals?
So this is common for this. Oh, no. This is common for all the materials, because in principle you are getting only the metal powder. See, you have put 80% metal powder, so you are getting 80% part. You put 65% metal powder, you get 65% part. So this is irrespective of what type of material you are using. It might happen that the process has some effect on the shrinkages that is subjected to research. It will be very vague to comment at this stage that whether it will be high impact or it will be low impact. The process itself, what kind of impact will it have on the shrinkage? But I believe that there will be some effect, of course, from the process perspective as well, from the sintering perspective.
So if there are any question, there is no question, I'll go to the proposed to vote of thanks. If there are any questions from the participants? Okay, I think,
From the chat box, there are a few questions.
yeah. Yeah, somebody have the same doubt. It's about blending the material with the polymer. He's not porosity strength. He's talked about porosity strength is very low. Yes, as professor said, it will tend to
Sir, I have a question.
Yes, Deepak.
Yeah. Yeah, I am Deepak Lawrence from NIT Calicut. Sir, we have two commercial manufacturers, Desktop as well as Markforged. Do you find any difference between the processes? Because they call it as two different processes for, yeah. So ultimately, both
Yes.
are having same root.
Yes, so I know about both of them, and yes, there is a difference. The difference will lie in how you are debinding the part. So in some cases, they are dipping into a solution, like what Markforged is doing, I think. In other cases, they are not dipping it in a solution. Instead, they are putting it into a gaseous environment. So there, the gas attacks the plastic part and eats it up. So yes, there is a difference, but that difference majority lies in the in how it is debound, and this debinding is directly linked to the filament composition, because in filament composition nobody will tell you about what is the exact filament composition, what is the proportion of the different components in it. So they will probably tell you that this is stainless steel plus PLA. But like I told you, that it's not just two components, there are also other components. So depending on how they have fabricated the filaments, what they have put inside the filaments, accordingly they will try to debind it. So some of them might get debined in a solvent, others might not get debined, others might require some presence of some gaseous environment. So in that way, these two, Desktop Metal and Markforged, they are creating difference, but everything else remains the same.
Yeah, sir, I have one more question. So
Please go ahead.
we are doing solvent extraction as well as thermal decomposition. So one to remove the binder, another one the polymer. So is it possible for us to combine these two? Because ultimately we want the sintering by atomic diffusion. So that way, can we think of something? Is it because we feel that these binders and polymer could be treated at once, maybe by some technique?
Yes, so that's a very relevant question and very good question. So there are papers where people have tried to do this. And so to answer this, so your part that you are having is first of all, it will have metal plus polymer and some other composition. So let's say you don't want to solvent debind it. Instead, you directly put it into the sintering furnace where you supply temperatures of 1200, because at 1200 eventually every polymer will eventually degrade and vaporize. So what will happen if you don't do the solvent debinding? I tell you, there will be no open pores on the surface for everything that is trapped inside to go out. So what will happen if you try to do direct thermal debinding? Then your entire structure will swell up, because there is, or blisters might form, because there is no escape route or escape path that is there. That is the reason why we are mixing different composition, because one part is being eaten up during solvent debinding, and this creates channels, this creates ways. So everything that is polymer and trapped inside the part can go out in the thermal stage when you apply the when you apply temperatures such as 1200 degrees or 1300 degrees, because if there are no roots, then blisters will form and it will get trapped inside.
Okay, so thank you.
Thank you.
Okay.
So if you have any
So,
questions, you can ask. Yes.
Yes, please feel free to ask, and also please connect on LinkedIn and try to join our short
Yeah.
course. It will be very informative and it will also be good for future collaborative opportunities. So once you are here at IIT Mandi, you'll be able to identify some internship opportunities, experimental opportunities, opportunities to write joint papers, and all these things can be discussed. So my suggestion is that please do register and try to attend that. And if you have
Yes.
any questions, of course, please, I'm free. Please go ahead.
Yes. If there are no questions from the audience, we can wind up. Professor, we are deeply appreciative of your dedication and commitment to delivering such an insightful lecture, even while you are unwell. Your resilience and effort are truly commendable, Professor. The presentation was very brief and informative for a research purpose. This lecture truly enriched us in wire-based, extrusion-based additive metal manufacturing processes. I thank you once again, Professor. I thank you all participants for patiently listening to the lecture for 1.5 hours. Thank you. Thank you, Professor.
Thank you very much. We may close the session now. Thank you.
Sure.